So I'm mainly an algorithm guy for electronic structure calculations. So what I actually do might be closer to you than what my affiliation might suggest. So also I quite hesitated whether I should give a talk on DMFT because this is really the audience on DMFT, and later I realized whatever, so I'll give this talk. I'd also tuned down a little bit the title compared to what's suggested in the program. Probably DMFT doesn't need much introduction, but still let me very quickly talk something about that. I want to get spectroscopy information, so we need green functions rather than just the density matrix. It's a type of quantum embedding methods from my home community, applied math, and we consider domain decomposition, but this is rather non-standard domain decomposition because it's a high-dimensional space. So you want to solve a high-dimensional, strongly correlated system by a series of low-dimensional impurity problems, and then you glue the impurity problems obtained from high-dimensional solution together using some sort of a single particle type of theories. So it's quite an honor for me to give this talk in front of this audience, because as you see from the references. So as DMFT has been applied to numerous strongly correlated systems, and I'm going to start by the algorithm part, which is our recent work just submitted the archive a few days ago. This is a joint work with Brigitte Willis group, and it's called a hybridization fitting. And what we want to do is for the so-called Hamiltonian-based DMFT simulation. So in order to solve this impurity problem, we know that there is some sort of H0 Hamiltonian and restricted to an impurity P, which is already of a small size. And then outside, the green functions will give you a hybridization function. So there are mainly two ways to handle this problem. One is you really treat it as an open quantum system. And let's say that we do the old-fashioned way on the imaginary axis, and then only at the very end you will do some sort of method to go to get the real axis information, because that makes the theory more well-defined. So then you can use quantum Monte-Carlo with a path integral, and there are excellent review papers on this topic. Or you can do a closed quantum system, or so-called Hamiltonian-based flavor of DMFT. To my knowledge, Dominic Usgid and Garnet Chen popularized this approach in the 2011. Many other people did similar things, and the advantage of the Hamiltonian-based simulation is really it allows a broader range of the impurity solvers to be used. Not only there's the quantum Monte-Carlo, but also you can use many quantum chemistry methods, configuration interaction, selected CI, coordinate descent, couple cluster, so on and so forth. But the disadvantage is that there is a procedure called hybridization fitting to be defined in the next slide. So hybridization fitting is basically you have a matrix, delta, I omega, let's say it's a n by n matrix. You want to factorize, it's a fitting procedure, factorize it into this form as a low-rank form, parameterize the low-rank form, H12, I omega, and running through the imaginary axis, I have assumed the chemical potential is 0, H22 inverse H21. So you can diagonalize this H22, which is a Hermitian matrix. Its eigenvalues are denoted by lambda, so you can put it on the denominator. Then on the numerator, you combine the eigen functions with this H12 and H21. You get this VL and VL star. Then you can unfold this function into a closed Hamiltonian system. I have to say, the first time I saw this procedure, I thought it was completely brilliant, and I've never seen how to unfold an open quantum system to a closed quantum system, not even the concept. And you put these V's here. It's only a quadratic interaction. So it doesn't actually introduce too much of the trouble when you solve the problem. And all the quartic interaction are embedded in this cluster. And so you successfully replace a large and possibly infinite-sized bath by a much smaller one, and sometimes by a very small one. So to summarize, and this is the form of the fitting, and you can treat V's are the fitting parameters, lambda are the fitting parameters. You can do a least square problem and try to solve it. Then you realize that the fitting problem isn't so easy because when you actually take for example, the Frobenius norm of the difference of the two, and this is already quadratic, so square that would be quartic. Furthermore, there's nonlinear behavior with respect to lambda down there. And it is very, very frequent that you will get into stuff at some local minimum. So quartic interaction doesn't sound too bad, but if we recall what happens with, for example, finding localized orbitals through some 1 year procedure, that's already quartic, and that's already very easy to get stuck. We have experts here in the audience, but now you put this thing here as well, and it's really very non-trivial optimization problem. And it is surprisingly time-consuming. So the first time when I heard the difficulty of this is through discussion with Brigitte, with some member in her group, Carlos, who's the first author in the paper. And he was saying that he launched like 100 random guess and try to hit 1 or 2, and that looks reasonable, and this is to be done at every iteration when you use a larger bath. And some of the calculations, 95% of the time is spent on this hybridization fitting. I was saying, no way. It sounds like, I mean, this is a quantum antibody problem. No matter what, the quantum impurity problem needs to be more expensive, but not necessarily the case. Maybe it depends on implementation, but that's what I heard at the beginning. So then got us a little bit interested and see whether this is really the case. So this delta z is a meromorphic function, and they're posed, and it's a matrix value. The poles are real, which is very important. Another signature of this delta is that this guy can be viewed as a positive semidefinite matrix. So it's just a residue, and residue matrix is PSD. That's also very, very important. And this is just to get you some idea that at least for equilibrium problems, we had some discussion on the first day about how to do similar things, or whether it is even possible for dynamics. The discussion was very inspiring to me, but at least just for thermal properties, you can absolutely do it. So our procedure is to seek for provably suboptimal solution, but at the expense of the optimality, we want to increase the robustness a little bit. So because you can define some sort of least square problem, but if you cannot solve it, then, I mean, that procedure isn't very useful. So let's say that whether we can just lose a little bit of the accuracy but make the procedure more robust than before. The idea is exactly as I said. So this one for each L, and this is a rank 1 matrix, and it is difficult to do, but I can do a standard procedure in convex optimization. I realize that this guy is PSD, and therefore I can relax this matrix to be just a PSD matrix at this positive semidefinite constraint. Then I realized that why this is good. It sounds like it's difficult because originally for each L, there are only, let's say, n degrees of freedom. Now it becomes n squared. However, the advantage is if you fix the lambda L, this becomes a standard semidefinite programming problem, which indeed can be solved much more efficiently. And in the case of quantum impurities, the impurity sizes are usually not very large. Let's say 2 by 2, 3 by 3, how about? And therefore, the SDP is actually is doable. So it's a very, very simple idea, and that's really the idea. So hopefully, with a relatively smaller number of NP, which is called the number of poles here, and then for fixed lambda L, and I can, this is the problem I want to solve, and which is, this is the discrepancy between the lambda and the fitting, and I want to minimize with respect to lambda L's and the XLs. So if this problem can be solved, I can always expand this XL using its low rank factorization. Here it is equal sign, but I can truncate the small singular vectors, singular values, and get a low rank form. And then I unfold this, so X becomes a U, L, U, L star, and for each of the rank Q, and then I get some effective bath. So it's a really straightforward idea. And of course, another feature, well, you can say either as a problem or a feature of the method, is that you're guaranteed that for all these Qs, or this NC, there will be NC copies of this lambdas. So originally, the fitting parameters, all the energies of the pose are completely distinct generically, but now by construction, some of them are actually the same. But later, we'll see that it's not necessarily a problem. The practical procedure is a nested optimization procedure. You minimize with respect to XL with fixed lambda L. Once this is done, and then you can compute the derivative with respect to lambda K following the Hyman-Feynman type of argument, because you have already optimized with respect to XL. So the derivative only depends on whatever things that explicitly depends on the lambda L. And then you can do the outer optimization, feed that using our favorite optimization, such as the BFGS. So the pseudocode for the algorithms is really simple, which means that you just relax it. You get some initial condition, which might be important. I'm going to talk about that. And you fix lambda L, you get XL, you get XL, you get derivative for lambda L, and so on and so forth. Okay, any question? Okay, so let's just show the performance for favorite benchmark problem, 2D Hubbard. And so impurity, there is the impurity solver uses from Brigitte-Willis group and developed in the past few years, and you can call it adaptive sampling configuration algorithm. It's a type of selected CI. You can use other versions of impurity solvers, definitely, such as recently developed the coordinated descent optimization, another version of selected CI, you can think, by Jianfeng Lu's group. So, but many others can be used as well. First of all, let's look at the fitting error. And so this is using the semidefinite relaxation. One feature is you can go to very large bath size, and still the error is very good, like 10 to the minus 6. And you can go for 2 by 2 size impurity, 3 by 3, or even 4 by 4. You can optimize this to be pretty well. And this is how the fitting goes. You can see that when you go to about 8 poles, essentially, there's the error is very negligible compared to the accuracy later achieved by DMFT, and similarly for larger. This is for diagonal. This is for off-diagonal. Actually, the off-diagonal elements, they are very difficult to fit, especially with the conventional brute force optimization methods. This is more, yes?
So what's NB effective?
NB effective is the total number of baths. So the reason why there's a difference between the number of poles and the number of total number of baths is because you have to unfold this thing. So for each pole, it corresponds to a PSD matrix. You do a low rank factorization of this thing. So let's say each of this L contributes NC, and just NC independent of L for simplicity. And so there will be NC baths contributed by each pole. And there's a little bit further complication because due to the sparsity of the 2D Hubbard model, only the boundary modes are going to contribute to the bath. So you just count, yeah.
But is this the number of impurities
this is the number of extra, yeah. The total number of sides we're talking about is 4 plus this NB effective. Yeah. So, and this is, to my knowledge, considered to be a large bath. So this is not what we use to do the calculation, just to show that the bath fitting problem can be done. Well, this is a more a fairer comparison in terms of accuracy and efficiency for the hybridization fitting. BFGS means you brute forcefully search for the optimized low rank form VL and the lambda L. This BOBYQA refers to the best method we had before, which is a derivative-free method to avoid getting trapped at the local minima. You can see that for small bath, I mean, you can somehow the SDR is remarkably already pretty good, and the accuracy is comparable. This one, as you can see, why they use the derivative-free methods? Because derivative methods it's very easy to get stuck somewhere that you don't like, but the derivative-free methods, the time is just ridiculous. Sometimes it takes more than 24 hours, and it just doesn't give you anything. When it returns you something after 40,000 seconds, it gives you 10 to the minus 2, while SDR gives you 10 to the minus 4. So it's really, I mean, the optimization is a very non-trivial problem, as I said. I mean, this SDR is provably suboptimal, but if it gets somewhere like this, it might be, say, it's better to have something than have nothing. So, what's the, let's measure further about the robustness. In convex optimization, there's often a flavor of theoretical result to be proved, which is, say, local minima or global minima or something like that, and becomes increasingly popular in machine learning. But this is not the case. So definitely, I mean, it's more robust, but it's not, I mean, you just close your eyes, you don't need to care about anything. This picture shows that the optimization problem for lambda may not be that bad. Let me explain what's going on. So we repeated, I think this is about 1,000 random simulation with random choice of lambda 1 and lambda 2. So it is very bad, no physical intuition whatsoever. And there are 2 poles, and this is 3 poles. And then you run the optimization. You say that if the error is smaller than some tolerance, and then we say it's a success, which is dark color. Actually, this is the error. And then when it is not successful, it is a bright color. You can see that there are definitely some non-trivial amount of the points that are bright, but they are mostly concentrated along the diagonal, which is very important, because along the diagonal is precisely the unphysical situation which you put lambda 1, lambda 2 to be very close to each other, right? So you are fitting 2 poles, you put them very close to each other at the beginning. Of course it's bad, because you know that there should be some spread of the energy. But as long as there's a little bit of a spread of the energy, you can see that it's actually quite successful. And then surprisingly, sometimes when lambda 1 and lambda 2, they're close to be quite close to each other, it's still quite successful. Similar story can be found in 3D. So it's completely empirical, but this figure also shows it's much better than you run 100 simulation and try to get 1 or 2 that works.
The color here?
Color, bright means bad, so dark means good. And so the...
But what is the color coding?
The color coding is the error of the figure.
Okay.
Yeah. Any other question? Okay. So, this is a self-consistent DMFT simulation. Shows that, when you increase the bath, is quite robust. And we tried before it was square, but now it's not a square, which means that there are less symmetries such as D4 symmetry that you can use, and this method still works. So let me, the remaining...
Wait.
Yeah.
This is Hubbard model.
Yeah.
Which temperature? What are which kind of clusters are we talking about?
Yeah, so the cluster sizes are this. I think it's a ground
What kind of cluster? DMFT, CA?
Yeah, I think it should be considered as a CDMFT, because it's not a single side.
So you can solve 8 side clusters at very low temperature with very good precision. That's what you're claiming.
I think this is what the code does.
I don't know, I'm just asking.
Yeah, I don't know. So as far as I know, this is what the code does.
Okay. I just
But is this cluster DMFT, or is this testing the fitting on a finite cluster?
Testing. This is cluster DMFT. This is not previously Aura just a fitting. That's why I can go to that increasingly large bath size. And this is really self-consistent DMFT simulation. CDMFT simulation.
And the solver?
The solver is ASCII. It's a type of selected CI.
And temperature?
temperature, I think,
Zero.
my understanding is 0 temperature, so as a ground state. Yeah. That's the easiest for CI type of methods. Any other question? Okay, so in the remaining time, maybe let me talk about some theoretical understanding. Many of them may not be new, especially physically to this audience, but nonetheless, I want to share some of our recent understanding and where we got stuck. So there are 3 things, and one is the so-called self-energy sparsity. Sounds like it should be a trivial issue to this community, but I want to say a little bit about that. And there's the so-called causality or well-posedness of the SF loop of the DMFT. Another trivial issue probably to this community, but got us stuck even longer. And then our understanding, some of our understanding for Luttinger-Ward formalism in the uninteresting case, which is Euclidean lattice field theory. So first of all, for the quantum impurity, for example, we consider the single impurity Anderson model. I like the acronym SciM, which is my home community society for industrial and applied mathematics. And the Hamiltonian looks like that, and there's the only non-trivial part is this U here. And then we know that the self-energy is a sparse matrix, and the only thing that is non-trivial is here. So the result can be very straightforwardly proven by diagrammatic arguments, and you just diagram and realize that this is the only thing with the I and the J index that connects to this one, and therefore it's done. But we actually thought a little bit further and realized, it's actually not so easy, because in many cases the diagrams, they don't converge, and as we have seen again and again and again in the past 2 days, and in many cases the resummation is needed, and or it's just a symptotic series. But this structure seems to be so robust. I mean, is there any non-perturbative way for understanding this sparsity? So I talked with a number of physicists and chemists and mathematical physicists, and realized that this seems to be a folk theorem. No, at least, I mean, at the latest since Feynman and Bernoulli, but presumably it's much earlier than that. And with the diagrammatic arguments, I mean, it's really the foundation of the DMFT, continuous time QMC, and so on and so forth for impurity problems. But we came up with, we think, should be pretty straightforward linear algebraic proof, and therefore it is completely non-perturbative. It's simple, but it's quite flexible, and therefore can be extendable to so-called classical impurity problems, which is Euclidean scalar field theory, which is completely asymptotic. The Feynman diagrams is really asymptotic, and it's actually a result you can think is for probability, quite interesting. And it also works for fermionic and bosonic system at the 0 and finite temperature, for non-equilibrium under certain conditions, and also for superconducting. So it's a very robust statement. Yes?
Sorry, nice question for that. I've not really understood. What is it? Sparsity pattern? What exactly?
Sparsity pattern is this.
What exactly is the statement?
Yeah. The statement is this. So the statement is the following. That is, the precise statement needs to be stated precisely for each case. But roughly speaking, is that when you have a non-quadratic part only applied to a subset of the degrees of freedom, then the self-energy will always be a matrix such that it is a 0 outside this sparsity pattern.
Okay.
Yeah. So which is of course expected.
And, well, I mean, I want to put a word of caution here. I mean, if you were to go from impurity models to lattice models...
Oh yeah, completely wrong. This is true.
Even without V, you could have a non-perturbative transition to a phase with a non-zero hybridization, which is the excitonic transition.
Completely agree. And this is just for impurity. Yeah, just
so it's trivial,
but the line which you have at the bottom says something else.
Oh, so sorry. Maybe I misunderstood. So sorry.
No, the last line says it's not for impurity problem. It's for fermionic, bosonic, high temperature.
Oh, they're all fermionic and bosonic impurity problems. They're all impurities. They're all impurities.
Well, it's written.
But superconductors require interactions in the system, otherwise.
I see. I see. So that was confusing here. What I mean is just when you have a BCS type of Hamiltonian. Yeah. So when you allow the particle numbers to fluctuate, that's all I mean. Yeah. So there's no non-trivial claims here.
Yeah, but the proof is sort of nice.
Yeah.
What is perturbatively trivial is not.
That's right. Yeah, because we know that 0 plus 0 plus 0 add them together may not be 0. It's just expand exponential minus 1 over x, right? Yeah. So I think just to say 0 plus 0 is not a proof by itself. Okay. Any question? Okay. Another trivial issue to this community is causality. So we can look at the Riemann representation, for example, for the retarded Green's function, and where you have this plus ieta. I mean, here makes the pose of the Green's functions to be below the real axis, or to say that the function is analytic in the upper half plane of the upper half complex plane. And so not only this issue, or so-called causality, is important for Green's function, but also important for other quantities as well. It's particularly related to the question whether the DMFT loop, once you do that, is well defined. So just to say that what is causal, and this is, first of all, it needs to be analytic in the upper half of the complex plane. And the second, even more importantly, the spectral density, or imaginary part of the Green's function, should be PSD. And it, of course, when it is PSD, implies that the diagonal is non-negative. Well, I found this issue, there are excellent papers written by people in this audience and illustrating in different scenarios why things are causal. But I have to say that from my perspective, it took me quite a while to try to even understand what is being argued there, because sometimes indeed the argument is applied to the diagonals, or the argument is directly proven for scalars, and it's hard for me to see whether the argument is straightforwardly generalizable to the general matrix case or not. But the question is indeed whether all these quantities, Green's function, sigmas, deltas, they remain causal in the SCF loop. For the imaginary frequency fitting, I think the word causality may be a little bit too general, because on the imaginary axis, we really don't care whether it's retarded or time ordered or any of these things, right? So what we care about is indeed whether a quantity is characterized by real pose and the residue matrix PSD. This is precisely what we care about, right? So more specifically, how causality matters in this scenario is that we consider the spectral density, which is a discrete PSD operator valued measure on R, which is you have some XL, and the only change is you remove the lambdas from the denominator to a delta function as a measure here. Then you do a SteelJS transform, but it's nothing but what you have seen before, so that make sure that this function class is some finite-sized matrix and some finite number of poles, and the residues are PSD. And this is what we care about. And in particular, we care about whether G's, sigmas, deltas, they are in this class. Okay, so I think this is probably a more clear definition of what we're talking about. Theorem, which is a working preparation, is that it's a very, it's more technical than we thought, which is what we can show is if at the pth iteration, the hybridization function is in this class, then at the next iteration, the hybridization is still in this class. What we cannot prove is when it converges, whether the converged delta is in some class, and why we cannot prove is because it is crucial we assume that K is finite. When it becomes infinite or continuous, which could be the case when it converges, we have no idea whatsoever. Okay, so it's to be clear what we're talking about. Although it might be true in physical, but we have no idea. This is the famous DMFT loop. The proof really you just follow step by step. So you start from H naught and on the impurity and hybridization, which is already in this class with a finite number of poles. You use some way to compute the G impurity. Then you do the inverse Dyson, get the self-energy, and then you put them together, get the lattice Green's function, inverse Dyson again to get the hybridization, and then you go back. And what you want to prove is when you go back, you're still good. Okay, is that clear? So there are 3 steps, roughly. First step is clear and Lehman. And when you have the delta, the hybridization is in this class, you want to show that the G is in this class. So Feta and Velasca. And the second step is that when you have G in this class, what is the class for sigma? Usually what I found in the literature, this is also considered to be a trivial step, saying that because sigma must be causal. Usually that's just a sentence. Took us a little bit to understand what precisely this statement says in a linear algebra setting. What it actually says is that is if you already have a function, which is G, in this function class, you assume the kernels, the intersection of the kernel is 0. You cannot apply to something that is not invertible. And then the inverse of that always takes the form of Zm plus C, where M is a positive definite matrix and G minus F inverse is in this class. And you can, of course, further prove that for in the present case, M, the static part should be Hartree-Fock. And that's
We're sort of entering discussion time.
Okay, so I'll try to wrap up soon. And the third step is to show that you get to the delta, and then you have another linear algebra type of thing to show that the function class is still closed. So I can talk more if you're interested after that. And then you couple all the things together, and you show that the delta is still in the same class. So I want to mention there's another thing we want to have in the paper is from this delta it's natural to have this continuous fraction representation. It leads to the so-called matrix product states representation of the DMFT as pioneered by Wolf and collaborators. But for the single side case, where to our knowledge there's a case, and we don't know for CDMFT whether this matrix product state approach has been developed. We haven't seen any because it requires a little bit of the so-called matrix orthogonal polynomials. Maybe it's trivial to the audience, but I'll be happy to discuss about that or let me know if this has been done. And it also gives you the possibility to do the so-called moment matching instead of doing artificial broadening. That's because moment matching is also another way of doing broadening. Let me use maybe, I don't know, a few minutes to...
Yeah, it's your call.
Okay.
We have 10 minutes till the end of the whole thing, including discussion.
Okay, so. So let me maybe use 5 minutes since I promised to talk about, quickly talk about our result on Luttinger-Ward. So well, let me directly say that the reason why I got into these things because of this influential paper is I was very excited when I saw the program that all the authors are in this workshop, and so because when I was first reading about when I previously have some work with the Steve Lewis group on GW, have heard about Luttinger-Ward as the foundation of this and that, and then saw this paper. Non-existence of Luttinger-Ward. So why? I mean, it's about the multi-valuedness, and many people in the audience have contributed to this issue. Illustrates why it gets worse and worse. So it's still a controversial issue. There is some faint hope this can be solved, but well, people seems to be pessimistic for good reason. So our maybe contribution is to say that to try to answer whether the so-called Luttinger-Ward functional mean anything. That's why we look at a much more mundane model called the Euclidean lattice field model, or you can call it Gibbs measure, which is look at the partition function, integrating Rn. So you have a quadratic part minus a u, which is interaction, let's say a quartic part. And you can make U to be quartic and mimic the Coulomb interaction. So there's a one-to-one mapping between the Feynman diagram of this and that used in the condensed matter, other than the particle hole lines. More specifically, for example, you can look at this quartic potential, and you're interested in the Green's function or two-point correlator, which has an important feature that it can be viewed both as a density matrix and as a Green's function, which is great, and which is absolutely crucial for us to proceed with the argument. And the original motivation for us was to understand Luttinger-Ward and also the so-called bold-Feynman diagram, which is very familiar to this community. And just to sum up, and what you actually do is that there is a Green's function insertion procedure, and you have some bold line, you insert a bunch of crazy things, and it means infinite many other things. So it really allows you to simplify the self-energy. So in particular, the second order expansion reduces from 9 terms to about 2 terms, including only the ring and the second order exchange. The foundation is the so-called Luttinger-Ward, and through a perturbative argument, and to our knowledge, never made rigorous. So first of all, since I don't have much time, let me directly go to this thing and showing that to our knowledge, so our work was the first time that the validity of the bold diagram is established ever. Please correct me if I'm wrong. Which means that we can have a non-perturbative construction of the Luttinger-Ward functional in this particular context, and to show through a non-perturbative argument that the Luttinger-Ward functional and its functional derivative sigma has asymptotic expansion, and then to show that the asymptotic expansion coefficient exactly coincides with that of the bold-Feynman diagram. And in particular, as a corollary, it recovers the famous relation between the coefficients of the Luttinger-Ward functional and that for the self-energy. So which bold-Feynman diagram explained in one particular simple, non-interesting setting. So there are many questions can be said. That's a short paper. We have 2 long papers currently in archive. So feel free to let me know if you have any question. And how to address the causality issue of the overlapping elements. And yesterday I learned this called nested DMFT. How to deal with the long-range interaction. And there is eDMFT, but whether there are better approaches. How to do this with the ab initio methods, whether diagrammatic is the right way to address the weak interaction. Why DMFT is good theory at all. I mean, usually this is referred to the Messner and Volhard paper at the d equals infinity, but maybe this is established, but I'm not completely sure whether it's the reason is really rigorously known. Sigma y has to decay faster than g as d goes to infinity. Whether one can fix the Luttinger-Ward for fermions at all, how to further increase the robustness of hybridization fitting to be really robust. The symmetry probably is an easier issue, and also there are some previously alluded directions we're currently looking at. Let me finally make some acknowledgement. Michael Lindsay, highlighted here, and he's a really brilliant student in the math department, but now I think he's at least in the math department, he's quite an expert now on quantum antibody thing. And he's going to be an NSF postdoc at Courant starting from this September. He visited here before. I very much encourage him to interact more with the Flatiron. I think he's a very good person to talk to. Leonardo Zepeda Nunez is currently a postdoc. He's going to join UW Medicine, the math department's tenure track. And so these are my chemistry collaborators, and these are the senior collaborators. Thank you very much for your attention.